Heard some Doc Edgerton stories. So this is the King Street Bridge I mentioned yesterday, I guess, and here is the weld detail on one of the girders that was holding up the bridge, and they developed a fatigue crack at the toe of this weld. Lots of restraint as you go around. Developed a fatigue crack, and then they had a brittle fracture go up through there. Okay. Like I said, no one got hurt or killed. In fact, as you look at the picture, the thing didn't even break all the way through. The top flange didn't break through the top flange. I had a similar failure for the George Washington Bridge in New York. It was a 9-foot crack and a 9-foot web, but it didn't fracture the top flange of the I-beam. It started at the, well, where did it start? It started at the bottom flange. Brittle fracture ran all the way up through the web, and the top one, because it was deflection limited, it didn't break all the way through. But they closed off one or two of the lanes from the George Washington Bridge coming into New York City for 6 months and created a lot of havoc. Okay, I wanted to talk about underwater welding, so we have a few divers here. I'm not going to spend a lot of time on it because there's not that much that I know about it. One of the problems is you can strike arcs underwater, or you can strike arcs at high pressure. We actually call welding arcs a high pressure arc, and when you take the fusion welding, I'll talk about what that means. But anything above a half an atmosphere in physics literature is a high pressure arc, and it basically means the electrons and the ions have the same relative temperature as opposed to a fluorescent light that doesn't. Anyway, it turns out the welding arc, shielded metal arc, gas tungsten arc becomes unstable at 450 psi or greater, and that's because as you increase the pressure on this thing above 1 atmosphere, you actually squeeze it into a smaller volume, and you get it down so it becomes narrow enough that the fluid flow, the gas flow in the arc becomes unstable, and it won't, it'll kind of get blown off to the side, okay, from the convection currents that are generated. Well, that means that whether you're wet welding or dry welding, you're limited with, if you can only go to 450 psi, and you really maybe can only go to 300 psi, you can strike an arc at 450, but it's not going to be a very stable arc. At 0.44 pounds per foot is the pressure increase of seawater, right? Did I get that as seawater right? I think that's right. I haven't looked that up for a long time. That means your maximum depth that you could do underwater welding at, whether you're dry or, well, a dry habitat or a wet habitat, if you're at seawater pressure, is 1,000 feet. Some of the dry habitats, actually, they have gone down deeper, because the dry habitats, they actually change the pressure inside the habitat. So it's really, you're welding inside a submarine, okay, if you will. It might be a stationary, it may not be a submarine that can move on its own power, but you're welding inside a dry habitat that can change the pressure. So the arc is constricted. That means that the heat intensity is different. So if you were to make a bead-on plate weld at 1 atmosphere and it looks like that, an underwater weld at greater depths might look like that, because the arc up here is much tighter. Up here at 1 atmosphere it's broad, up here at 20 or 30 atmospheres it's narrower. You get a different shaped weld pool, okay? Now if you're only welding at 100 feet deep, you have a hard time telling the difference in these things. But if you get down 500 feet or something, you get enough pressure, you actually start seeing some differences. You actually ought to be able to see it at 100 feet because that's 6 atmospheres. The weld metal chemistry changes. There's a lot of chemical reactions going on in here in the weld pool. One of them is simply CO plus carbon goes to CO2, okay? Oh no, that's not the way it goes. CO plus oxygen goes to CO2, and there's an equilibrium between the CO pressure and the CO2 pressure in the welding. Actually, that's not the one I wanted to write down if I had to look at my notes. It's carbon dissolved in the steel. We put an underline among steel metallurgists, gives you CO. And so you actually, with higher pressure, you'll drive that reaction back this way. you'll retain more carbon. You also retain more manganese and silicon. You'll get a richer weld metal chemistry if you have everything the same, if you're at higher pressures. And it's noticeable. I mean, your carbon content could be, instead of 0.1, it could be 0.14. It could be a 40% increase. Your manganese and silicon might go up by 20 or 30%. Your welding chemistry changes. And so those people, Barco or whoever you said it was, Barco have adjusted their weld compositions. And I don't know, they may even sell for different depths, electrodes for different depths. I don't know, okay, but okay, maybe they don't, but there's been plenty of work, not that much work done on underwater welding metallurgy, but it does change the chemistry, and it changes it to a more hardenable chemistry. In addition, if you're wet welding, you're welding and you're quenching this whole thing in water immediately. Okay, you're using, the arc itself will generate a pressure, and it can generate up to 30 atmospheres to push back the water, but you're welding in a humid atmosphere is full of hydrogen. So you're full, if you look at this old type of plot, okay, of this, or Venn diagram circles, you have more hardenability because the chemistry changes. You have a very high hydrogen environment, and depending on what you're welding on and the amount of restraint, you've got a fair amount of stress. And if you're doing this as a repair, emergency repair weld, for example, was it the coal that had the big hole in it, and we didn't want the terrorists out there in the Gulf to think they had destroyed a U.S. capital ship, so they actually went in and they had to do underwater welding. It wasn't very deep, it was just down, to the keel beam and stuff, and they towed it back and they repaired it. They could have bought a new ship for less. They wanted to prove that some terrorist with a motor launched skid didn't destroy a U.S. capital ship. Okay, so they repaired it, but it was an expensive repair, and they couldn't have even gotten it back. Just the seas would have torn it apart. The damage was severe enough. They had to have some weld repairs before they could even tow it back to the U.S. Yes.
They put it on a heavy lift ship.
Oh, they did?
Yeah.
Okay. Well, there's another one that we had bombed. Anyway, that they had to do something, but they may not have even been able to get it on the heavy lift ship.
They may have had to make repairs in order to have it loaded.
Yeah, to get it up. So, anyway, but dry habitats, you can get around the quenching, you can get around the hydrogen problem, and as you said, Tom, you said most of the time the Navy goes to a dry habitat. Well, dry habitat's a lot more expensive. The barge costs typically for doing underwater welding are on the order of $100,000 to $1 million a day. And if you're talking about, well, and a dry habitat is closer to the million than the 100,000. Just to do a wet weld very deep, like a couple hundred feet deep, you're going to be paying for a barge $100,000 a day. And of course, at 200 feet deep, a diver can go down and up in a day. Okay, at 800 feet deep or something, you can't just go up and down in a day. You actually have to be pressurized in a chamber before you go down, and then when you come back up, you have to be depressurized in that chamber. And sometimes those chambers can take up to a week.
Yeah, so that specific type of diving called saturation diving.
Yeah.
The Navy really doesn't do it. They essentially did it as a proof of concept.
Right.
But commercial divers do it every day. But yeah, down at, I think the deepest saturation dive is kind of like 1,300 feet.
Feet?
But typically, people don't go down that far.
Yeah.
800 to 1,000 is probably about the deepest most people go. And the decompression time is about a week.
Right. I mean, they put you in this chamber, and the chamber is still at 30 atmospheres, and they have to change the atmosphere. In fact, the Navy did all this basic research on the metabolism, and they have to have mixtures of helium and oxygen, and and they have to change the gas chemistry because your blood chemistry is working for some equilibrium at approximately 1 atmosphere, right?
All the diving space stuff, U.S. Navy research, but we don't do that type of diving typically.
Yeah, well, you don't want to put people in harm's way, right? Contract out some idiot. I'm sorry. Some sucker. Whatever you want to call the person, okay? It's very hazardous work, but there's some people who just love it, okay? I can't remember. Somebody yesterday told me, I was mentioning I was looking for my underwater welding notes, and one person said, oh, his cousin wanted to be in underwater welding, or something. Okay. It is sort of neat, but it's sort of a specialized technology. The oil companies with the offshore oil rigs do it all the time. And so there are big companies down in Louisiana and Texas that are have these barges, and saturation diving means your blood is saturated with oxygen and stuff. And most of you have seen from the movies about the bends where you can get too much nitrogen in your blood, and as you come up it gets saturated with nitrogen. As you come up, it's just like the CO2 coming out of the Sprite. The nitrogen comes out and all of a sudden you have a two-phase blood, nitrogen and liquid, and it doesn't flow the same, and you get the bends and you die. Does anybody know where we first discovered the bends?
Brooklyn Bridge, caissons.
Yep, Brooklyn Big caissons. Very good. How'd you know that?
I'm also a diver.
Oh, okay. Were you going to say something? Yeah. Oh, okay. To build the Brooklyn Bridge, which was sort of a major engineering feat at the time, the caissons, they decided that they basically floated a structure in the Hudson. It is the Hudson on that side, or that's the East River. Anyway, whichever river. And it basically was a diving bell type of structure that they put down on the river floor. Actually, it went up. So this is the river, and they went down to the river floor, and they had some hatches here, and people would go down. They would pump it out, pump the water out. They'd have air, compressed air coming in, and people would just dig down. And this caisson would slowly, very heavy caisson, would sink down into the mud. And these things went down like 500-600 feet or something. I don't remember. But they just, a bunch of men in there with shovels, and they would go down and work with little miners' helmets and stuff with air blowing in. Pretty miserable type of environment. But they noticed some of them, as they started coming up, as they were getting deeper down, they were starting to get cramps as they came up. And that's when people learned about the bends, okay? They were getting deep enough, they were breathing regular old air, and they would get the bends. It was like 1880s or so. It was back in the 1880s. Has anyone had altitude sickness? If I go out to, you've had altitude sickness? So what's it like? Where were you?
I was up in the Rockies, up in the Pac Northwest.
Right.
And it's, I don't know, I'm more susceptible to high altitude. Just like, it feels like you can't breathe completely.
Yeah. And you get worn out if you try to exert yourself. I have some children who went to school in Utah, and I go out there regularly, and at 7,000 feet it doesn't usually bother me. We went up to Sundance once to watch a play one summer, and your blood chemistry changes in about 3 days. So this usually occurs, your body will adjust to the lower altitude pressure, but at 8,000 feet it's like 0.75 atmospheres or something like that. I don't remember. So you're not getting as much oxygen. You feel tired, and if you do try to exert yourself, like you say, you're not getting the oxygen your body was used to, and it is, I don't know if it's genetic, but certain people get it more than others. I don't get it so much. I don't notice it all at 6,000 feet. At 7,000 feet, sometimes when I'm out of shape, which I am all the time now, I can notice it. But when I got up to 8,000 or 9,000, I just lay down. I didn't watch that outdoor play. My children and my wife were I just laid out on the grass, and we almost had to get a cart to take me back down. Okay, and I think we parked at about 7,000 feet, and we walked up to 8,500 or something. By the same token, if you just kind of quickly, I've been over passes in the Rockies at 10,000 feet, and I didn't notice anything, although if I'd stayed there for a little while, because it doesn't hit you right away. It sort of grows on you the second day or so. But by the fourth or fifth day, you get used to it. in general. So that's altitude sickness. Well, welding has altitude sickness too. It turns out Denver is the Mile High City, and they developed a process to make nuclear warheads at Oak Ridge in Tennessee, which is, I don't know, less than 1,000 feet, probably 500 or 600 feet elevation. And then after they developed the process, they took it to Rocky Flats in Denver, which is now the Denver airport, okay? And they went to put it into production. And it turns out the atmospheric pressure is 0.82 atmospheres or something, as I remember. And so it didn't work the same. The shape of the weld pools and stuff weren't the same, okay? When you lost 20% of your pressure. And they actually had to put the whole thing in a pressure vessel and pressurize it, and they called it pigma welding. If you look in the literature back in the early 80s, you'll see papers in the welding journal. This is gas metal arc welding, pressurized inert gas metal arc welding or something like that. I don't remember but it was called pigma welding. And they didn't exactly explain why they were doing it, but the scuttlebutt is it's because the Department of Energy developed it at Oak Ridge and moved it up to 5,000 feet, and the arc characteristics changed enough. So pressure does affect arcs, okay? But you have a lot higher pressures in underwater welding. Any questions? Yes? Yep.
Yeah, do you mind if we talk about the heat affected zone a little bit with the quick quenching? Just, I read a lot about that because we were concerned with changes in water temperature and their effect on welds. It appeared over the years that if you made a weld in really cold water, then it tended to crack out a lot more than one made in warmer water. So looking at some of the research that people have done, they focus on the time between 800 and 500 degrees. Right?
That's not the reason, but go ahead. I mean, yes, I'm sure a lot of people probably said that.
Yeah, please
Oh, no.
Please
Okay.
understand it.
Yeah.
And they found that between 80 degrees, which is some of the warmer water that you could probably ever be in, and 30 degrees, some of the colder water you'd ever be in, that there wasn't a significant difference between those two times. So it really didn't matter. Either way, you're going to produce martensite.
Oh, yeah, okay.
Exclusively. And for our case, assuming that martensite, what BCT form of martensite is not what we want because the lattice structure in the carbon, right?
Right. Okay.
People had kind of hypothesized that it wasn't a delayed cracking issue, but I kind of took exception with that.
You were right.
The Welding Journal article that said that the way that the cracks presented themselves wasn't consistent with hydrogen embrittlement or delayed cracking. So,
Okay.
but I didn't believe it. Because I think what's happening is hydrogen is getting forced into the weld pool from the dissociation of water.
Yep.
And my thought was that at the lower water temperature, hydrogen wasn't absorbing back into the water, surrounding water, and it was getting forced into the weld.
It's getting into the well pool at a very high saturation, but it's not escaping. That's the problem. Okay. If I look, so that other comments? Now let me expound, okay? So if I look at a welding heat cycle and I go up to 1600 degrees centigrade, actually T800, 500 is actually Fahrenheit, okay? If I remember. No, it's centigrade. It's centigrade. So this is my CCT curve in general, and let's look at this. What temperature is it? We should be at 800 to 500. I must be. This is in Fahrenheit, so in centigrade, this is where I'd be transforming up in here, 800 to 500. And you're right, we talk, welders like to talk about the time to cooling, delta T is T 800, 500 in the welding literature. And that's because that's how long does it take for you to get through this transformation region. And if it's a simple carbon steel, it takes, you got to get through there in less than a second. Do they put time scales on here? So you got, this one is actually slightly alloyed. Oh yeah, it is slightly alloyed. It's 8630 steel. So slightly alloyed steel, if this was a carbon steel, you'd have to get through there in half a second to not get martensite. Or not to, wait a second. You'd have to get any depth of hardenability. But this one's got some depth of hardenability, so you're going to get a higher hardness heat affected zone. And so it's the 800 to 500 that people like to talk about, welding metallurgists like to talk about. And that tells you, gives you some idea of how long your welding process, your welding heat is. And with the whole thing quenched, you get through there a lot quicker because this whole cooling thing, I mean, you basically go up about the same in a wet weld, but you come down a lot faster. Okay, you're quenching down a lot faster. You have a shorter T85, and people worry, metallurgists are trained to worry about that T to 85 cooling time. Okay, well, you're breaking down water up here, so you're in a 60% hydrogen atmosphere. And I don't care whether you're at, if you're at 800 feet, you're in a 60% hydrogen times 25 atmospheres, which is a very high hydrogen potential. You can pump more hydrogen in at higher pressure, so it depends on what depth you're at, but you're going to cool the same. The steel, once you start throwing water on hot steel, this cooling curve doesn't change because of depth or anything like that, but you're trapping in lots of hydrogen, more than you would at 1 atmosphere because of the higher pressure. However, the problem really is at these other pressures, what happened to my Sprite? When it was pressurized before I popped the cap, there were no bubbles. There was no CO2 coming out. At higher pressures, you're going to keep the hydrogen in. So it was hydrogen cracking. First of all, was it delayed? Probably. It may not have been delayed as long. It might have been tens of minutes rather than a couple of hours because you had a higher hydrogen.
Well, they're acid etching cross sections anyway, so it's
Right. So it's delayed. Yeah. So first of all, it was delayed cracking. That's hydrogen. I don't care what anyone else says. If it's delayed cracking, it's hydrogen induced. Why is it hydrogen induced? Has nothing to do with the high temperature stuff other than in wet welding, I've just got lots of hydrogen present, more than enough for virtually any steel. I quench and I'm going to get martensite, so if I look back at my Venn diagram, which I don't have here anymore, it's a problem. Now, why cold water? Well, I actually told you this. Okay, this is for stress corrosion cracking, but I showed you a similar schematic, but this is one. Well, cold water, I hold the hydrogen in. The time to failure goes up by a factor of 2.5 from warm water, right? So there you go. I mean, it might take less time because you got more hydrogen, but it takes longer time because you're cold water. So cold water, maybe it still takes an hour or two before it cracks. But it's delayed cracking. You're right. You were right. It's hydrogen. Okay? Go back and rub their noses in it. Right? But the reason, and it really is the difference between, there is a difference between cold water and hot water. Okay? But that's because of the hydrogen diffusing out, not because of something going on up here, but something happening out here, much longer time. This is like 10 seconds. I mean, the hydrogen cracking is out here, tens of minutes or hours. Okay? Does that all make sense? Okay. See, you learn the principles and you can figure it out for yourself. In fact, I haven't given you that little lecture of mine, but the first day I didn't give you the full lecture. I don't really care whether I'm telling, and you can tell I don't really care whether I'm talking about welding or brazing or dock edgerton or anything else. I actually look at teaching as trying to help you learn to think through an answer, with the idea that most of you actually have all the information you already need. Now, I might be given, in welding, I might be giving you this, but hopefully you'll get some of this stuff and you'll be able to leave here actually having enough information and figuring out how to put it together, okay? And you can actually, the world is not that complex. If you can ask the right question, then you often can figure out things yourself from the first principles. So the first principles here is delayed, it's hydrogen. Does temperature have an effect? Yes, it does. I showed you the V-shaped hydrogen diffusion out, so that makes sense. If I actually went through the heat flow stuff, which we haven't gone through, but you will get later in the fusion welding part, you can figure out that changes up here are really not that significant. Other than, you know, if you have depends on the hardenability of the steel. Some steels might make a big difference, but in general, this thing is quenching so fast in water that no matter what type of steel you have, you're going to get martensite in wet welding. Okay, so there are lots of problems with wet welding, but you know, sometimes you have to do it. You don't have a choice, so far as that goes. There is a story about, it's actually a joke. It doesn't really have a moral, but actually it does have a moral, so I'll tell it. There was this new preacher in town, and he went to church that first day, and he'd worked very hard on his sermon, and he's waiting for the parishioners to come in, and the only person who shows up that Sunday, because they hadn't had a preacher for a while, one old farmer comes in and he sits in the back of the room, and so the preacher waits and no one else shows up. It's time to start, and he goes up, walks to the back of the chapel, and he says, well, what do you think I ought to do? You're the only one here. And the farmer says, well, if I had a cow and she was hungry, I'd feed her. The preacher thinks, well, this is a good philosophy. So he goes up and he gives an hour and a half sermon that he had prepared. And afterward he comes back down and he says to the old farmer, he says, well, what'd you think? He said, I said I'd feed her. I didn't say I'd give her the whole load. So anyway, you don't have to give them everything all the time. So I didn't give you, I told you I had a lousy attitude about the way we teach. And most people try to make you think that science is, or whatever they're teaching is complex. I think it's better to teach you that it's actually simple, okay? Maybe it's just because I don't understand it myself. And here, okay, here's my pointer. So let's talk, I did leave something off on one of my, before I went to nickel-based alloys. This is stainless steels in called critical pitting temperature. And 316 stainless steel has got a critical pitting temperature around 10 degrees centigrade, okay? And this is as a function of molybdenum content. 20 CB3 is a steel made by Carpenter Technologies. This is welded and unwelded, so 20 CB3 is 30 degrees unwelded. When you weld it, because of segregation in the welding zone and changes in the welding microstructure, you'll get pitting at a lower temperature. If you add more molybdenum, you got 316, 317. Should have been a bigger change there, but in any case, about the best, and at temperatures, how hot does it gets to about 37 degrees centigrade in the tropics in the seawater, doesn't it? Something like that. Okay. I remember a story that when they were building the Nautilus, designing the Nautilus, their heat flow calculations of how much heat you could dump in the tropics for the air conditioning system varied by a factor of 5. I mean, they didn't have fancy computers and stuff, and they didn't have all the boundary layer theory that was going to tell them how well the seawater could cool things on the sub. And so they went to Rickover and said, well, what do? We got a variation of 5, and you know, the heat exchangers are going to be huge at 5, and you know, it's going to change the ship design. He was being conservative. He says, allow for 5, and it was just barely enough air conditioning. Okay, so the Nautilus could operate in the tropics, but if they hadn't, they would have been limited to certain latitudes, northern or very southern latitudes. In any case, I told you the Navy was interested in making an all stainless steel submarine, and the alloy they were looking at was Al6X, which is 6% molybdenum And molybdenum is a pretty pricey alloy, so this was going to be a very pricey stainless steel. And you can see the reason is, unless you stay in the tropics for a long time, you wouldn't have pitting problems with a very high molybdenum content, because you are going into a salt solution. Okay. So, okay, I just wanted to show that there is some corrosion on stainless steels that relates to the Navy. Now let's talk. We talked about nickel-based alloys. Oh no, we haven't. Yeah, we talked. No, we haven't talked about nickel-based alloys. So I was going to talk about nickel-based alloys today. What's all this stuff? Oh, this is the rest of my notes. Yeah, I was going to talk about nickel-based alloys. I forgot. I put my notes over there. These are the notes. So I showed you Cedric's little genealogy of iron chrome alloys, and if you go up here and you go to a higher chrome, and eventually you go to what we call the Inconels, which are nickel chrome iron rather than iron chrome nickel. So nickel becomes like 60% of the alloy, so far as that goes. So you can think of that as an extension of stainless steels. Some people do call the nickel superalloys a class of stainless steel. A lot of times they just call them high alloy, or they might call them high alloy steels. Some people say if it doesn't have 50% iron, it's not a steel, okay, because steel is an iron-based alloy. But some people throw the Inconels with 60% nickel in there and 20% iron as a steel. But most people just call them high alloys, whether they're steel-based or nickel-based. There's also cobalt-based, but cobalt, most of the world's cobalt comes from Zaire, used to be the Belgian Congo, because they have very good cobalt deposits. Cobalt's expensive anyway, but the supply out of Zaire has been very erratic for the last 80 years because of fighting going on and stuff. So people have been trying to get cobalt out of alloys for a long time. HY 180 is like a 10% cobalt alloy. Landing gear steels that the Air Force developed, AF 1410, is 10% cobalt, similar to HY 180. You can get very high strength, interesting hardening. Cobalt is the only element that actually can change the martensite start temperature in the opposite direction. Everything else, as you alloy, you lower the temperature forming martensite. Cobalt actually increases the tendency to form martensite. And so it's unique, but it's also expensive and very unreliable supply. If I want to look at nickel and nickel-based alloys, there's commercially pure nickel, which we use for some corrosion resistance when we have hydrochloric acid or something. Nickel is, but it's not a long-term problem. But if you have hydrogen chloride gas or not too concentrated hydrochloric acid, you can use pure nickel. Easy to weld, almost like welding copper, easier than copper because it doesn't have this high thermal conductivity. But then we have the solid solution strengthened alloys. And this first one, nickel copper alloy, is actually called Manel. And most of you have probably heard of Manel because the Navy still uses a lot of Manel. Manel is a 70% copper, 70% nickel, 30% copper alloy. And here I turn the thing off again. Here is Ambrose Manel. Okay, so he was basically the person who founded Inco, and his name is M-O-N-E-L-L. The alloy is M-O-N-E-L, and that's because the trademark office said you couldn't trademark the name of a living person. Okay, who cares? Turns out he developed the 70% copper nickel alloy. It turns out that it's, which is Manel, named after him. He went on to find, actually, he didn't found Inco. He founded Inco. The other guy who was famous in the nickel business is Elwood Haynes, who founded Haynes Stellite. Okay, but Manel was a British subject in Canada, and there was a particular mine in Sudbury, Canada, that had 70% nickel and 30% copper in the ore. And there's no coincidence that Manel discovered an alloy that came directly from the same types of concentrations that they had in the Sudbury mine. Had excellent corrosion resistance so far as that goes. Later people developed nickel molybdenum alloys. These are the B hastelloy Bs, nickel iron, nickel chrome iron. These are actually sometimes used for toaster oven filaments, okay, or heating filaments. Very, very good high temperature strength and resistance, corrosion resistance, oxidation resistance. Nickel chrome moly tungsten, nickel chrome iron moly, nickel chrome cobalt moly, okay. These are all solid solution strengthened, and we still use these particularly in high temperature or corrosion resistant atmospheres or situations. Precipitation strengthened, we actually start adding aluminum and titanium to these things, or sometimes niobium, and we vary these things, and these have very high temperature strength. Your turbine blade alloys are typically made out of these things. Many of your Inconels have these. Some of these are the Inconels, some of these are precipitation hardened Inconels, where you can heat them up to high temperatures and then do other things. Turns out nickel and aluminum form a nickel 3 aluminide that melts at 2,000 degrees centigrade. Nickel melts at like 1650 centigrade, higher than steel, but not much higher. But the nickel 3 aluminide melts at 2,000 centigrade. And same thing with nickel 3 titanium. Okay? Nickel and titanium love each other. Nickel and aluminum love each other and form this ordered intermetallic. In fact, I was once asked when I consulted for this gold company down there back in the early 80s, they said, well, can you develop a harder white gold? Because people were choosing white gold for their class rings, and so they wanted a hard white gold that wouldn't be too soft and wear out. And so I looked, turns out white gold is just gold, copper, silver with some nickel in it, like 10% nickel. And so I was teaching thermal at the time. I took my phase diagram books home, and I looked at it and I said, add, I don't remember, 0.2% nickel to your white gold, and then heat it up to this temperature to solutionize it, quench it, and then heat it up to this temperature, intermediate, and see if you can get precipitation hardening. 450 Vickers.